Good morning. Let's begin today's discussion with continuous probability distributions, and we will focus our discussion today on exponential random variables and normal random variables. So, an exponential random variable x satisfies the following property, which says probability of x being greater than or equal to t plus s given x is greater than t is nothing but the probability that x is greater than s. What this is really called the memoryless property of the exponential distribution. So the way to explain this is, if a machine has worked for 20 hours, what is the probability that it will work for 5 more hours? So the fact that this machine has worked already for 20 hours has no bearing on the fact that the probability that the machine can work for 5 more hours. The probability that it will work for 5 more hours will simply be probability that x is greater than 5. That is what is known as the memoryless property. It does not remember how long it has worked. For example, if you take a light bulb does not know that it has been working for 20 hours. So if you want to find the probability that it's going to work for 20 more hours, it does not mean you're calculating the probability for x greater than 40. You're really computing the probability for x greater than 20. The past does not matter, and we use this property in stochastic process a lot, and it is known as the memoryless property of an exponential distribution. Let's take the example of time between arrivals at a bank, which can usually be modeled as an exponential random variable. If you want to find out probability that x greater than 40 given that 30 minutes have passed, then all we need to do is find the probability that x greater than 10. If we say that 30 minutes have passed since the last customer arrival, what is the probability that it will be 10 more minutes before the next arrival? So all we need to do is compute the probability that x is greater than 10 and not worry about the fact that 30 minutes have already passed since the last customer arrival. So what it is if you take this as t and this as s, the probability that x is greater than t plus s, which is here, this probability, given that x is greater than t, given that x is greater than this amount here, is nothing but probability that x is greater than s, or simply x is being greater than 10. So if you want to find this probability, all you need is to simply say probability that x is greater than s. Now there are several practical applications for an exponential distribution. Let's take a few of those now. Let's take a look at a few of those now. uh, Time it takes for your next phone call. It doesn't matter when you received the last phone call. So time it takes before your next phone call is from the current moment until however long you want to measure that interval for. Then time for the next customer to arrive at a bank. Time taken until you default on a debt. uh, the density function for an exponential random variable looks as follows. F of x is lambda e raised to negative lambda x. Remember the lambda from the Poisson distribution. This lambda is also nothing but the rate of arrivals of customers, or rate of arrival of phone calls, or rate of arrivals of bits of information. Lambda can be a rate of any event happening or not happening, and lambda is usually a number which is strictly greater than 0, and this is also generally known as a negative exponential distribution. It's also called a negative exponential, but we usually just call it the exponential distribution, and there's a density function. It only exists in the positive space between 0 and infinity, and it is 0 everywhere else. Here is a quick example of exponential random variables. We have been given that the mean of the exponential random variable x is 32 minutes, and the mean of exponential distribution is nothing but 1 over lambda, and which is 32, so which means lambda is nothing but 1 over 32, and we are being asked what is the probability that x is less than 30 in this case. That's just not written here. This will be posted, the actual problem is available online and you can take a look at it. But all you need to do is really integrate the density function lambda e raised to negative lambda x, where lambda is given to be 1 over 32 between 0 and 30. So it's just like any regular probability density function. If you want to find uh, the probability that x is less than 30, you simply integrate it between the limits between 0 and 30, since this function does not have anything in the negative space. An exponential distribution also has an interesting property. There's a relationship between Poisson and exponential that we will utilize in this particular example. So what is the probability that there will be exactly 2 calls in the next 1 hour? So here they're asking us a discrete question based on a continuous random variable. So how do we answer those type of questions? Because in the previous thing we said, in the previous part of this example, we talked about receiving phone calls uh, in the next half hour. So uh, how do we handle the scenario where if we are being given an exponential random variable, but the question is a discrete question? So Poisson random variable and exponential random variable have a very interesting relationship. If the number of phone calls to a switchboard are distributed Poisson, then the time between phone calls the time between phone calls is distributed exponential. So we can use this idea to answer this question. So we can actually use the information that we have to find the probability that this y random variable is 2, and use a density function of a Poisson random variable, which is lambda raised to x e raised to negative lambda divided by x factorial. And all we need to do is find the lambda, which is 1.875 in this case, and x, which is 2, and we'll be able to find the answer for this. And the way you get this 1.875 is nothing but we are saying that lambda is 1 over 32, and that is in hours, and if you want it in minutes, that'll be 1 over 32 times 60, and that would be 1.875. So if you're wondering how this lambda value of 1.875 has been obtained, that's how it's been obtained. And if you have to find how many calls in the next hour, then all we need to do is, this is really 1.875 per hour, that's how many calls per hour. That's the lambda value for the Poisson distribution is 1.875 per hour. So we're really switching these 1 over 32 by multiplying it by 60 into how many phone calls are there per hour, and we have been asked to find the probability that y equals 2, and all we need to do is lambda raised to x e raised to negative lambda by x factorial. Your x or y variable, it doesn't matter, is equal to 2. So 1.875 whole squared multiplied by e raised to negative 1.875 divided by 2 factorial, and that happens to be negative 0.2696. In the next module, we'll take a quick example and solve for a normal distribution.